Good morning, everyone. I am Prithivirajan, presenting AI-driven software-defined networking for automated threat response. Traditional security takes 4 to 6 hours to respond to attacks. We reduced into 8 to 12 seconds using AI and SDN. Let's dive into it. Here is our roadmap: introduction, problem statement, scope, methodology, architecture, algorithm, design, implementation, codes, result, test cases, conclusion. We will cover all key points briefly and focus on results. The problem: traditional security is re- reactive, static firewall rules, manual alerts, isolated tools, attackers spread while analytical investigation. Our solution is AI-driven SDN NFE combines machine learning anomaly detection with centralized network control, results in real-time automated test response, 40% reduction in latency, self-healing mechanism. Challenge: response latency from 4 to 6 hours by then damage is done. Objective: design AI SDN framework achieving 50 ms interference latency, 90% true positive rate, 40% reduction in detected latency, 4 to 6 hours to 8 to 12 seconds. Autonomous containment via VLAN microsegmentation. Scope of our projects included rear REU SDN controller with OpenFlow 1.3, ML model development, Flash REST API, flag-based microsegmentation, production production deployment, customer OpenFlow modification, SIM integration. Methodologies: phases approaches of methodologies: data collection from OpenFlow switches, pre-processing, normalization, ML model selection like uh, random forest, isolation forest, modulus SMB, LOF. Model training with scikit-learn, REST API development via Flask, end-to-end testing and evaluation. Here is our architecture diagram of our project. Bottom with connected with Mininet plus Open vSwitch network emulation. Left side of our diagram is Review SDN controller with OpenFlow controls. Center of the diagram will be our API call, Flash API with random forest model. Right side of our document is a VNS service, PF Sense Firewall, and surrogate IDS. Our flow of architecture will be traffic switch API detection, drop rule, VLAN isolation. Nextly, we are move on to use case diagrams. Actors will be network security administrator. Use cases will be configure SDN controller, monitor flow statistics, trigger API model training, detect anomaly traffic that are automated, apply containment policies that also will be automated, view alert as logs, analyze performance matrices. This is our use case diagram. Nextly, we are move on to class diagram. Key classes are anomaly detection trainer, train models, select best models, AI anomaly, API, Flask REST endpoints, predict health info, microsegmentation controller, queries API, install OpenFlow rules, network flow collector, gathers real-time statistics. Sequence diagram. Sequence of our project will be flow arrives from the switch, rear controller pulls statistics, extract feature, duration, packets, bytes, rate, size. Post to AI API, random forest inference, Response: attack or begin. If attack, install drop rule plus VLAN 999. If not, a log a event. Totally 8 to 12 seconds. Algorithm used. We have evaluated 4 algorithms: random forest, isolation forest, one class V SVM, LOF. In this 4 model, random forest will be best, and random forest is uniquely balanced accuracy and speed with 92.3% accuracy, 93.1% TPR, 4.2% FPR, 50 seconds training model. Implementation stack. Network stacks used in this project: language Python, web Flask RESTful, data pandas and NumPy, ML training models, skyscraper, SDN, View Controller OpenFlow 1.3, network Mininet plus OpenVSearch, VNF PSense Surrogata. These are the important codes. This is for model training. This is for API called Flask API. This is for microsegmentation using VLAN. Let's start our project demonstration from now.
Let's move on with the deployment and demonstration process. Here we running the AA API script to turn on the AA API that we used for this project. And the AA anomaly detection API is run and waiting for request on port 5000 on local. And on the other terminal, we are running the review manager in which we have the real controller setup, a custom made for this. And the thread is started and waiting for switch to connect. And on the next terminal, we are going to run the mininet topology on the localhost IP 127.0.0.1 with port 6633, which OVS Open Virtual Switch. And the topology is created with H1, H2, H3 and switch 1 and all links connected to it. And we have a virtual VNF host and VNF IDS host. Now when we look back into the view controller manager, switching is connected now. Then a flood attack is planned to be posted in the mainnet. From H1, a flood attack on this port 80 with synchronization flare. Now the flood mode is active. And when we look into the review manager from 192.168.10 to 192.168.11 on the port 80, heuristic DOS attack is detected and it is blocked. Okay, I forgot to turn on the dashboard Python 3. The dashboard shows the A detection API is online, exchange control is online, and VNF services are online, and shows that the flow analyzed as Benin from the beginning, and the thread detected as DDoS, like we said like this, and we look into the A API. Only the Benin health status from the dashboard is showcasing here because every DOS flood is blocked by the review controller and it is mentioned here. And in the dashboard, the host is quarantined also. Then we move on to the next.
Here is our results of our projects. We have high accuracy rate with 92.3%. We have high positive rate 93.1% and less false positive rate 4.2%. Our F1 score will be 0.92. AI latency, which is traditionally 50 milliseconds, because now our project will be have 23 milliseconds. Our response time will be 8 to 12 seconds. Our conclusion of our project will be what we have built: AI-driven SDN NFV architecture that detects and blocks network attacks automatically in 8 to 12 seconds. Key achievements are 92.3 detection accuracy, 8 to 12 second response, fully automated, no manual intervention, all test case passed, production ready system. Our impact will be transform reactive security into self-defined networks. Future works of our project will be ML enables random forest plus XGBoot plus neural networks, multi-control SDN for scalability, real NFV deployment, not emulator, closed loop learning, production database plus uh, SIM integration.